Evi Murgia is a senior hydrogeologist with 10 years experience. She's completed both her master's and bachelor's degree at WMU while performing research on contaminant fate and transport in fractured bedrock aquifers. She has worked on numerous hydrogeologic studies across the state of Michigan, focusing on projects related to PFAS and other industrial contamination, high quantity water withdrawals, coastal erosion, and glacial aquifers. She has experience working on large-scale projects across academia, government, and industry, and additionally teaches introductory earth and environmental science courses at Kalamazoo Valley Community College. So she will be talking to us now for a while, and at the end, we will be having questions and answers, okay? That's the format. And that's all yours. Thank you.
Okay. Well, speaking of teaching intro geology at KVCC, I want to first thank you guys for having me, but also for those of you that have your cameras on. My students never want to turn their cameras on when I teach online, which is fine, but it feels nice to be able to actually present to something that doesn't just feel like I'm talking into the ether. So thank you guys for that. And then additionally, I find that it's really difficult to get professors to talk for less than an hour at a time. So I'm going to try my best to stay on timeline today, but we've actually got a good bit of material to get through. A lot of it we're just going to scratch the surface with. You guys have had an introduction to what I'm going to talk about. And like I said earlier, I'm probably going to be preaching to the choir a little bit here. So I'm not going to spend a ton of time on what climate change is, the evidence that it's happening. I don't think that I need to say that to this particular crowd. Things that we're probably already familiar with: rising global temperatures, sea level rise, melting ice and snow, extreme weather events. That means both more extreme cold and extreme hot. So we're expanding our spectrum of options, and we're having more of a bimodal distribution. So we're more occurring on these ends of the spectrum. And then ocean acidification and issues with mixing as well. So these are all evidence that climate change is occurring, as well as symptoms of increased carbon emissions. So because I'm also a teacher, I kind of want to give you guys a bit of a context. And this is where I hope that I can give you something that helps you explain it to other people. So we're going to zoom way out from Michigan and Michigan's water resources and consider our solar system first. You may or may not have heard of Milankovitch cycles in the past. These are what gives us natural climate cycles. Now, when I talk to my students, not many of them remember a time when there was a very common argument in the news for, oh yes, global warming is real, but it's natural, it's fine. The Earth has had cooling and warming cycles forever. And this is whatever's happening right now is just part of what we're supposed to be experiencing. And there's nothing we need to worry about, and there's nothing we need to do. You guys remember that? Yeah. There's some truth to that. There are natural warming and cooling cycles. However, importantly, according to those cycles, we're supposed to be in a cooling period right now. We're not. We're in a warming period. So I want to kind of give you guys some background on that. All of these Milankovitch cycles, there's 3 different types: eccentricity, obliquity, and precession. All of these describe Earth's position to the sun. That's important because depending on where Earth is relative to the sun will change the amount of UV radiation that is reaching the Earth. So eccentricity is a measure of how elliptical Earth's orbit around the sun is. So it goes from more circular to less circular, and this will change on the order of about every 100,000 years. It's rounded. All of these figures are rounded. Never quite reaches a perfect circle, but it's not a very dramatic ellipse either. It's near circular on both extremes. Obliquity is going to be the tilt of the Earth, right? So this is what gives us seasons when we're tilted. That's why we have opposite seasons between the North and the South hemisphere. So when we're tilted towards the sun, we're experiencing summer. When we're tilted away from the sun, we're experiencing winter. And so we will vary on the order of about every 40,000 years between 22.5 degrees and 24.5. We're at 23.2-ish right now. And it will go back and forth between those two. And then precession ties into obliquity in that you guys remember taking a coin and you spin it on a table as fast as you could when you're a kid. Right before gravity takes hold and it's about to fall, it does this sort of wobbling thing. Earth is spinning, right? It's stuck in this perpetual state of wobbling. So the more dramatic the angle the Earth is tilted at, or the obliquity, the higher the obliquity, the more dramatic that wobble is going to be. So if we have a short or a small angle, it's a little bit tight wobble. If we have a big angle, it's a more dramatic wobble. And it's not that huge of a difference when we think about it in reality. But it does, those two are tied together. And precession is going to be the most frequent on the order of about every 20,000 years or so. The reason that we know that this exists is because of what's called the Vostok ice cores. So this is a huge project. You guys maybe have heard of it. There's been a number of projects where they drill into Arctic ice. This is the main one that gives us this data. So you'll see in the picture here, this is an ice core that they've drilled down and retrieved. And this is a zoomed in photo. So every single one of these little blobs is a gas inclusion of ancient atmosphere. This isn't a direct measurement. This is a proxy measurement, but it gives us a pretty good idea. Proxy in the sense that if your odometer comes or goes out on your car, but you know that you drove about 12,000 miles a year over the last 2 years, you can probably still figure out with good accuracy, reasonable accuracy, how many miles are now on your car if the odometer went out 2 years ago. That's kind of what we're working with here because there's some degradation of those gases over that time. It's been a long time since these gases have seen the surface, but it gives us a good idea of what the conditions of that ancient atmosphere were like. And then additionally, and this goes back about 420,000 years on the ice cores. Additionally, it is that evidence of what those ancient atmosphere conditions were like are corroborated by gas inclusions in salt cores as well. That's a very different depositional environment, right? So with ice, it has to be cold, it has to be wet. With salt, it has to be wet, but it has to be hot and it has to be cycling between wet and dry so that the salt can evaporate out of the water and build those deposits. That will also include gas. Those don't go as far back in time. They go about 2/3 of the way of this timeline that we're considering here. You guys can see my mouse, yes? Okay. But it corroborates the salt cores corroborate what we see in the ice cores. So it's a pretty strong line of evidence. When we look at the actual data from that, black line here is going to be the temperatures. Blue line is methane. Red line is carbon dioxide concentrations when we look at those gas bubbles. And what you'll notice from this is if we look at the scale of time here, that when we hit these peaks, all of these peaks kind of line up. See these high peaks? So when carbon dioxide and methane concentrations are high, temperature is also high. That's not a surprise. What we see with the Milankovitch cycles is that if you'll notice these super high peaks line up with roughly every 100,000 years. That's eccentricity. We can also see obliquity and precession in this, which brings me back to, according to that, in those natural climate cycles, the Milankovitch cycles, we're supposed to be entering a cooling period right now. However, we are not. We are currently entering a warming period. So the previous figure, we're focusing on a timeline of the order of hundreds of thousands of years. To understand why we're going into a warming period, we need to cut that down and zoom into the last 200-ish years. So if we're looking back 2020, back to 1750. This is just carbon emissions, not methane or temperature. We can see a little uptick start right around 1830-ish. So anybody remember what historical event happened? I'm so used to interacting with my students on this one. I'm asking for audience feedback. Industrial Revolution, right? The answer is right there. I try to do that for my students too. You'd be amazed how often they don't get it when the answer is right there in front of them. But so this is the innovation that puts us into an entire new chapter of human history. It is also what leads us into a new chapter where we have climate issues and climate change. Probably preaching to the choir here, but a good way to think about the greenhouse effect is that it is a positive feedback loop. A lot of people are surprised to learn that carbon dioxide is not the most abundant greenhouse gas. It's actually water vapor. Now, that doesn't mean that water vapor is bad, okay, but it is the most common or most abundant greenhouse gas. And then we have carbon dioxide, methane, among others. And what happens when we release an anthropogenic amount of carbon dioxide into the atmosphere, that increases the overall amount of greenhouse gas. The greenhouse gas is what traps UV radiation coming in from the sun. Again, that Milankovitch cycle is coming in because the Milankovitch cycles are the position of the Earth relative to the sun, which changes the amount of UV radiation reaching the Earth. Okay, greenhouse gas is the local contributor to that, the amount of UV radiation that is trapped in the atmosphere. So if we increase carbon dioxide, we have more greenhouse gas overall, which means we're getting more UV radiation trapped in the atmosphere. More UV radiation means higher temperatures. What happens to water if you heat it up? It evaporates. So that's going to send what into the atmosphere? Water vapor, which means now we have more water vapor, which is a greenhouse gas, and more carbon dioxide. So if we have more of both overall, that's going to trap even more UV radiation. And then if we trap even more radiation, the temperature continues to go further up, which means we evaporate more water and the cycle continues. That's that positive feedback loop. It's not a very favorable snowballing effect. A little bit of a transition here. I want to talk about the terms environment and sustainability. We often see these together, and they're coupled together for a reason. There's two different focuses between environment and sustainability. You'll see these together in articles, in organization titles, in college titles, in program titles, in contingency planning, everything. They're always coupled together, generally. I shouldn't say always, they're generally coupled together. Environmental is going to be focused strictly on the environment, and sustainability is what takes into account the social, economic, and environmental needs. So it's not necessarily all environmentally friendly solutions are also sustainable for human activity. So when we talk about our future, what we really have to consider is the sustainability of those options. Sustainability implies a balance between conservation and consumption, which is just a necessary part of our future. We are consumers, we are people, we use energy. It's the modern world that we live in. The trade-off of that is going to be our limited resources, namely water, and then others, namely critical minerals. So we're going to talk about both of those today because they go hand in hand. Now, to give us some context on the global water crisis, I think it was Marianne said that there's an idea that Michigan just has this wealth of freshwater resources, and in a sense we do, but it's not necessarily what it may seem from the outside or non-locals or people that don't have an understanding of this information. So when we think about water, a lot of people will say, well, we just have so much of it, right? The 70-ish% of the Earth's surface is covered in water. We think about all the water on Earth, 96%, 96.5% is going to be saltwater, saline, ocean. So when we're looking at this very small percentage of what is actually freshwater, it's 2.5%. We split that up. We're looking at what's actually accessible to us. Most of it, right, nearly 70% of it, is locked up in glaciers and ice caps. Those are melting, which makes it available, but it's melting into what? Saline water, which makes it also saline water, which makes it not usable to us if it's just melting into the ocean. So what's usable to us is going to be groundwater and then surface water and other fresh water, like the Great Lakes, for instance. If we split that up further, right, we're getting smaller and smaller and smaller percentages here. Then on the surface, we also have permafrost and direct ground ice that's going to melt and fluctuate with the season. So it's not always available, and it's also at the surface, so it's susceptible to surface contamination as well. Same thing with lakes, rivers, streams, swamps, marshes. That's an even smaller percentage. And then we have some in the atmosphere, and then we have the smallest part in living things, so us, right? When we think about the world's use of water, we use it in some of our most important, societally important functions. So we can kind of split this up into agriculture, that's this black and dark blue. That's the majority of our water consumption globally. And then we have municipal, which is going to be this red and gray, that's a smaller portion. And then industrial, which is this green and yellow. So it goes majority, agricultural, then industrial, and lastly, municipal or private water supplies. So individual people-ish in communities. Does that mean we can stop agriculture and industry and private water supplies? No, we can do things to control our water consumption, but this is what we're looking at right now. As you can imagine, as the population continues to grow and climate change continues to amplify, these conditions are expected to worsen and our limited resources will be depleted. So I'm going to show you quite a few global maps, and some of the things I want you to pay attention to. This one is showing water stress predictions for the year 2050. This is from the United Nations Global Report. Gray is going to be areas with no data, and then as you can imagine, red and orange are going to be the ones that are worse off or more stress by 2050. Yellow and light yellow are going to be less stress. And then gray is no data. Notice there's no areas with no stress on this map. So let's look at the areas where we have this high stress. And you might look at this and think, okay, well, there's a lot of areas where there's going to be pretty low stress, so we can just use those areas. Well, we have to think about where people live, where people can live, and where people have historically lived. So when we think about that, it's going to be areas with higher population, higher water stress, and in environments where we can build. So there's resources for us to be able to build a city. There's areas where we can access the resources, the water resources for people. So when we think about the desert where nobody lives, maybe there's not that much high stress, but that's because there's nobody consuming water there because we can't live there. Now let's zoom in back to Michigan. Michigan is poised in a unique position because it has a complex geology. And that complex geology translates to a richness in resources. That's both water and critical minerals. It's not an exact split, but we can loosely split it between the Upper Peninsula and the Lower Peninsula. The Lower Peninsula is defined by this complex glacial geology. That means that we get a bunch of sediment that was dumped out by glaciers tens of thousands of years ago. So that's a lot of sand, and that's a lot of clay and some gravel. What's nice about that for groundwater and surface water is that we can have aquifers in the sand layers, or the mostly sand layers, and then we often get protective layers of clay on top of that. It's really hard for contaminants to penetrate and travel through thick layers of clay. So we end up with naturally protected aquifers that don't have to be engineered, they're naturally that way. We also have a ton of surface water bodies. It's over 11,000 inland lakes, and of course we have our Great Lakes. And then below all of that glacial sediment, we have what was previously a marine setting back when you guys remember plate tectonics, everything's moved around over time. So back when Michigan was a lot closer to the equator, its environment was much more similar to that of, say, a modern Dominican Republic, okay, or wherever you want to go on your tropical cruise. That's pretty similar to what Michigan used to be. So think beaches, and that's why we have a bunch of bedrock in the lower peninsula that is sandstone and limestone. And the sandstone can make a really good aquifer. We also get shale from that, which can make another protective layer because that's something that's hard to pass through. And so we end up with that in combination with the Great Lakes, we end up with a lot of high quality aquifers compared to the rest of the world. With the UP, we have a whole suite of what we would call critical minerals, and I'm going to come back to this. Many of you may be aware of the historical mining that has taken place in Michigan, and a lot of those things for metals like copper and nickel and iron all originated from the UP, and that's part of what made Michigan such a good place for vehicle production is access to loads of water for the industrial processes, relatively close access to all of the metals that are needed for that, and then additionally relatively close access to their market. So going into the rest of the Midwest and to the East at the time. So to talk about clean energy, we need to first talk about energy use. As of 2019, 84% of our energy, global energy, was produced by fossil fuels. So it's oil and gas, it's coal. And then when we look at this yellow portion, that's going to be not necessarily our non-renewables, but altogether that 16% is our what we would call low carbon emissions options. Split that up. So I'm taking the 16% and going over here. 7% globally is going to be from hydropower. 5% combined is solar, wind, bio, tidal, and geothermal. So all of them together, only 5%. And then 4% from nuclear, okay, which is not renewable, but it is low carbon emission. The path forward with energy is electricity. And that's because that's what frees us from, or has the option to free us from the use of fossil fuels. Notably, a lot of our current electricity is produced from the burning of fossil fuels, 63% in 2019, 27% from renewables, and 10% from nuclear. Now, this is growing from 2000 to 2019. We've increased quite a bit in terms of nuclear and renewable energies or renewable and recyclable energies. At the same time, our energy use and overall need has also increased. So from just 2000, that same period, 2000 to 2019, we've increased our usage overall by 73%. Okay, which means even at the rate that we are expanding our renewable and recyclable energies, we are not catching up. It's not proportional to the amount that our need is also increasing. So we're dealing with a battle in a couple different senses here. Clean energy is this overarching term that encompasses both renewable and recyclable energy. So when we think renewable energy, we're talking about things that don't require limited resources. So hydro, tidal, solar, wind, biofuel, and then recyclable energy is going to be nuclear that's up to 95-ish% recyclable. Hydrogen, I have an asterisk on, I'm going to get into that momentarily. And then waste heat recovery. So it's important when we talk about clean energy to understand exactly, are we talking about renewable energy? Or are we talking about recyclable energy? Because they all get lumped together as clean energy, which is defined by low carbon emission options, but that doesn't necessarily mean that you're talking about renewable energy. So there's a distinction between those. Now, I'm going to go through each of these and we're just going to scratch the surface. And I want to preface this by saying that there are positive points for all of these. I'm going to harp on the negatives and the risk that they pose to water resources in particular. But there are positives to all of these. So when we talk about solar energy, this is one of the top options that are considered in the general public for moving forward for renewable electricity production. Something to keep in mind with these is one, they're quite difficult to recycle. So once their lifetime is over, which 20-ish years, it's really hard to extract the precious metals from that and to reuse it, which means that they often end up going to a landfill. These are produced with heavy metals like cadmium and lead and arsenic. So if they're not stored properly in a landfill or they're not maintained in a field properly, they can leach contaminants like those heavy metals wherever they are left. So in some cases, that's rooftop buildings. In other cases, it's not uncommon for it to be an agricultural land. If there's incentives for farmers to use solar panels, they may opt to do that instead of producing crop with the idea that they might be able to return to crop production. If there's contamination at the surface and there's runoff from that as well, then that gives us issues with being able to return to crop production. There are different regulations on maintenance of solar panels depending on where you're at in the world, which state you're in. Michigan's rules are pretty conservative, so it's not as much of a concern here in Michigan, but again, we're talking at a global scale. The solar panels also sometimes require chemical cleaning. So they can't have a layer of dirt and dust on them, even if they're in agricultural lands with heavy winds lifting up all of that dirt, because they won't be able to get the sunlight. So sometimes that requires cleaning with heavy duty solvents and detergents, which can also pose a contamination risk for runoff. The other part of this is the level of power is unreliable, meaning you need it to be sunny in order to get solar power, right? And again, it requires the use of critical minerals for construction. When considering wind energy, we have a lot of the same concerns. They're also difficult to recycle. They require a lot of maintenance. Their lifetime is also close to 20-ish years, but if they're not properly maintained, they're more commonly only reaching 6 to 7 years. It's also dependent upon their size. So they have a limited lifetime. They're also difficult to recycle, and they also require the use of critical minerals. So we have these turbines that are turned by the wind. That has to get converted by a generator. That generator has to have magnets in it. So that's where those critical minerals are coming from, amongst other construction components. There's also a lot involved with trying to get it connected to the power grid, and that process also uses or can use freshwater resources depending on where these are set up at. Additionally, just like the solar panels, there's an unreliability to that power source because you need it to be windy in order to get wind energy. When we talk about hydro and tidal power, there's a couple options for these. Hydropower is something that you might be more familiar with. It's dams, hydro dams, movement of water, we're capturing it. That's the theme of both of those. For tidal power, this is a relatively new innovation that's being tested in a lot of areas right now. It's not really commercially applicable yet. But there are a variety of ways to either basically have like the equivalent of a wind turbine, and this would be tidal energy that would act in the same way as the wind turbines, but instead of air moving them and turning them, it would be water moving and turning them. And then we have wave energy, which is where we get something that floats on top of the waves in an area where there's going to be fluctuation up and down, and then a piece that will anchor it to the floor so that you end up coming up and down, and that will connect to a generator that can then turn that energy into electricity. Issues with this is that for hydropower in particular, if we need to build a dam, or clear land or do anything of that, as you might expect, that can cause disruption to local eco and river systems. That can also cause disruption to individual people's water sources. So I've worked on a couple different projects where I was assessing risk of either removing a dam or installing a hydropower dam and how that would impact the local water table and whether or not that would cause regionally everyone that lived around the lake or river um, for their wells to run dry, which in these rural areas where they're usually happening can have a really big impact on individual families. Wells are not expensive. I mean, they're not cheap. They're quite expensive to install. Maybe $30,000, depending again where you're at in Michigan and how deep you have to go to get to that water source. And if their well runs dry because of that change in the local water table, then they have to pay more money to either drill a new well or drill deeper in their current well, which is not a cost that we want for Michiganders. With these, we can also have issues with eutrophication. So we get algae problems if there's just poolings of standing water. That bacteria has a better chance to build than if it's flowing. So if we're building a dam and we're capturing it somewhere, that's another risk that we run. And again, there's some unreliability to the level of power with these. You also run the risk of damage and extensive maintenance if these are offshore machines and you have hurricanes that are also perpetuated by climate change. They're in salt water, so there's corrosion is going to happen at some level, which requires additional maintenance and replacement of parts. And as you might guess, these also require critical minerals for construction. Biofuel energy doesn't have the same caveats as the previous ones that we've talked about, but it does have its own. So this is not as popular of an option yet in the US, but other places in the world, particularly South America, have a lot of regulatory incentives to do this. The downsides of that is that depending on those incentives and how they're written, it can sometimes lead to deforestation of areas that we would otherwise consider a carbon sink. So they're able to take in carbon, they're able to hold that in the trees and the soil, which means that we can end up with what's called a carbon debt from that land clearing. And they clear that land and deforest so that they can grow particular types of crops that are best for biofuel. And those particular types of crops are usually water intensive crops additionally. With these products, and depending on what they're using as the biofuel, we can have release of nitrous oxide, nitrates, and methane. Animal droppings or manure can also be used as a biofuel, which can release methane. And then if we have a ton of one particular type of crop in an area, that would be a monoculture. And this is something that just from an agricultural standpoint, we do have in Michigan, where we're growing too much of one crop at one time in one area that requires a particular set of nutrients. And we can supplement with fertilizer, right? But then that has its own issues with potential surface contamination and pesticide runoff. But if it's one particular kind of crop, and it doesn't matter what it is, it could be soybean, corn, whatever, it has a particular need. It's drawing all of that from the soil. If you grow that too much in one area, it's going to leach. It's going to pull all of that particular nutrients from the soil, and you won't be able to grow that crop anymore. That's why you'll often see crop cycling between, most commonly, corn and soybean in Michigan, is because they can kind of exchange between what types of nutrients they need and allow rebuilding of the nutrient that it didn't need for the other crop to come back in. But if we're doing biofuel energy, then it can strip, depending on what's being grown, it can strip the soil of those essential nutrients and not be used in the future because it's a short-term vision to just grow that, get the biofuel energy, produce it, get the monetary incentive. Nuclear energy is something that's still used today, used to be more common. The concerns with this are probably more obvious to the general public. We have radioactive waste from this. Some of it can be recycled. The trouble with it, or the difficult part with it, is in storing it and storing it safely. It stays radioactive for a very, very long time, way longer than we'll ever be here. Not just us in our lifetimes, but several generations to come. So there's some risk in storage. Has to be the right geological environment, has to be the right containers. And we don't have a lot of materials that can be used to store it that will last as long as the material is radioactive. Most things will break down before that uranium breaks down into something not radioactive. So it makes it difficult to store it long term. We have a lot of solutions that can buy us time on the order of up to hundreds of years. So that gives us time to kind of figure something else out. And then we can pick particular geologic settings that make it more difficult for it to potentially migrate far out. But there's not an end-all be-all solution to say we're going to put it in this one spot and it's going to stay there forever and it's not going to leak at all. We don't have that. We probably all heard of some pretty severe accidents and then some complications or issues or attention to how this technology can be used in other ways that maybe aren't beneficial to society. The other issue with this is not just on the energy production itself, but on obtaining the uranium in the first place. Uranium mining uses a ton of water in its process, and it also very commonly can lead to both water and local water and soil contamination. It can be done safely, but again, we're talking at a global scale, which means we're dealing with different regulations in different areas, and different protections to the communities that are surrounding these deposits. Hydrogen energy is not as new as it may seem. It's been around for decades. The considerations for hydrogen use are that it's either done through electrolysis, where we pool hydrogen from water, we separate the hydrogen from the oxygen. And that requires a lot of energy input in the first place. So in order to get this energy out, you do have to put quite a bit of energy in the first place. If you're going to be starting with salt water to be able to desalinate that and then separate out those molecules. Can also be done by steam methane reforming. And this relies, of course, on methane, as the name suggests. So we're separating, in the previous case, we're separating it out from water. So hydrogen and oxygen in this case, we're separating it out from methane. And then this process also requires a lot of water for cooling as well. So water use is just inherent to the process of producing hydrogen energy. In quite a few of these options, I talked about the reliability. And with the modern world that we live in, that's something that has to be considered when we're looking to energy solutions. On the left here is what's called the duck curve. So this is what we get from solar energy. So as you might guess, we're getting the most solar energy at the time of day. So this is what ends up being pulled from other sources. So this would be, say, from like Consumers Energy or another provider. So in areas where they have a bunch of people with solar panels, they're going to be providing 500 around the morning, and then as the sun starts coming up and it gets more intense, again, weather depending, then the need from the power company will reduce, but then in turn, they end up with much higher energy needs in the evening that are all going to peak at the same point, which puts stress on the grid, which means that we need more infrastructure. More infrastructure requires more materials, which also requires more mining. So it's this kind of complex, multifaceted issue that we just keep peeling these layers of the onion back. And then the point of this one is to show that the wind energy is going to vary incredibly, not just by season, but by day or by hours. So there's not a lot of reliability in that. The solution to being able to have this range and reliability of energy resources is to have good storage, right? So if we have a bunch of good batteries to hold that solar energy that we get in the middle of the day, then we don't have to get the other energy from the power company from burning fossil fuels in the evening. The production of the storage for energy also requires critical minerals. There's a list of about 50 globally accepted critical minerals. Each country will have their own list. Each state has their own list. But generally, these are the agreed upon. So the critical ones are going to be the ones in red on this graph. There's other ones that we use that are less critical as we move out to green. Those big ones in the energy storage production are going to be lithium, right? Lithium ion batteries, nickel, cobalt, graphite, the list goes on. To get all of these minerals, we have to mine them from deposits. There are deposits in different areas of the world. These mining operations are often large scale. They can require dewatering, meaning that you have to move the regional water table quite a bit to be able to dig down without your mine flooding. So that could be moving a bunch of water to the surface and trying to redeposit it into surface water bodies like lakes, rivers, and streams. The issue with that is if you take water that's been protected in the ground from human activities for the entire time that humans have been doing things, and then bring it to the surface and have it run over the surface, it's going to be exposed to all the things that humans have been doing, and that puts it at risk for potential contamination. Then you're redepositing it into the surface water bodies, and then that can percolate down eventually to those groundwater resources again. So we end up with, right, we're talking about the water cycle now. This potential risk that we're pulling all this water out, we're exposing it to contamination, and that poses a risk there. Or locally, if they don't discharge it back to natural streams, they'll keep it in water retention ponds or mine tailings ponds. If those aren't not properly maintained, then we're taking all of that water that was moved, mixing it with all of the waste product from the mines, which often are going to contain a ton of heavy metals, which are not good for our water. Then they can, once they get wet and they're exposed to the oxygen in the air, will undergo different reactions that can produce additional toxic waste like arsenic and other things that we don't want in our water. And this is another one of those things where it's the level of regulation is different. So the level of protection is different depending on where this is done at. And a lot of the areas of the world where we have these deposits are in areas where there's minimal regulation and maximum profit to be able to extract these. Let's zoom in on Michigan. Again, this is mostly the UP, but we're very lucky to have a wealth of these resources where we have very good water resources and we also have a ton of critical minerals. So little known is that the UP has some of the best copper mines in the world, meaning the cleanest and richest deposits, meaning the most bang for your buck if you're a miner or developer. You don't have to do nearly as much work, and you don't have to dig up nearly as much volume of material to be able to get a high quality, dense copper out of that. Minimal processing costs, minimal construction costs for the mining. We also have a ton of iron. That's not as common a practice to mine anymore. We've got coal, natural gas, oil and gas is also common in the Lower Peninsula. So those same geologic formations that allow us to have good aquifers in some areas of the state allow for good oil storage in other areas of the state. My former colleague, Dr. Autumn Hagsma, I believe, spoke with you all recently about carbon capture and storage. It's again those same geologic formations that pose potential or have potential for carbon to be stored because they have space within them. There's tiny spaces in between the grains of the rock where we can have any kind of fluid. So that could be carbon. When it's under enough pressure, it turns into a liquid. Or excuse me, CO2. That could be water, and that could be oil. Could be natural gas. So we have a good opportunity for that in the Lower Peninsula. And then the Upper Peninsula could be copper, iron, silver, gold, nickel. We have a ton of options in Michigan. Again, while there's a lot of opportunity in that, it's important to consider the ramifications of all of that development. Additionally, Michigan is considered a future climate haven. And I'm noticing the time, so I'm gonna speed up a little bit. But we're expecting to have a lot of climate migration over the next 50 to 75 years as temperatures get hotter, um, conditions get more extreme along the coastlines, sea level rises. We're pretty safe here, and snow is also decreasing, so it's becoming more tolerable for people from warmer climates. We don't really have earthquakes. We will continue to get more tornadoes, but in comparison to people who live in Tornado Alley, it's comparably pretty safe. So we're expecting, and then of course our wealth of resources, we're expecting a lot of climate migration in the next century here towards Michigan. Back to the global picture, when we look at all of these critical minerals, we're looking at all of these circles and they're proportional to the wealth of deposits there. So again, just looking at the overall locations, we can see that these overlap with some of our more at-risk communities. And then we have this coloration from the light beige all the way down to the red, and that's showing political conflict. So there happens to be some decent overlap in areas of mild to severe political conflict with some of these rich deposits, which, as you can expect, means generally less protections for the communities where this would be mined. For risk of climate change, we're looking at an overlap. You're going to see red in a lot of the same general areas on these maps. So we have most of our risk around this area for climate, and that's partially calculated by, it's partially informed by what is going to happen with climate change, the sea level rise, increased weather events, increased temperature, but it's also dependent upon the resilience of the communities or the countries. So do they have resources for that? Are they working towards climate action planning? Those kinds of things. How tolerable are those changes going to be? And then when we look at our global ecologically sensitive areas, these are going to be areas where we have the naturally occurring infrastructure. So rainforests, trees, soils that can absorb carbon, areas that we would generally want to protect as carbon sinks to be able to naturally absorb that carbon. We don't have to do any special construction. We don't have to do carbon capture, storage, and utilization in these areas. That also happens to overlap pretty well with these areas where we have these critical mineral deposits that would require deforestation to mine, and where we have these at-risk communities for climate change. This is probably starting to feel like quite a big and complex problem at this point. Decarbonization is still the way forward with this, focusing on electricity as the energy source. Again, there were positive points I harped on the negative. I was beating down all of these energy sources for the last hour, but there's positive points to all of these. And while innovation is going to be the key to finding solutions moving forward, I'm going to back up to the Milankovitch cycles and the Industrial Revolution. This is where we need to consider the ramifications of innovation. And part of that solution is in diversifying our energy portfolio. There's a variable reliability in all of these. Some of them require, they all have different caveats. Some of them have overlapping caveats. So the more options we have in the low emission category, the better, so that we don't get too wrapped up in one option and then have all of the consequences of that. So what can you all do? This is a very big global problem. It's many of the things that you're already doing. That's the local activism, that's participating in trying to change regulations, that's having influence where you can. That's at your local level. Then looking to state and federal, vote accordingly, and with enough communities doing local activism and voting accordingly, the hope is that that can propagate to a larger level and eventually globally. And then we talked about Milankovitch cycles in the solar system. So I threw in one more level to this, and I don't think it could hurt to wish upon a star. So with that, I think I've eaten up almost all of the time. So I think we have a few minutes for questions. I'd be happy to answer anything you guys are thinking about.
Okay, Tim.
Thanks. I would appreciate it if once again you would emphasize, as you have, that we need to transition away from use of fossil fuels, in spite of all the challenges of doing so, which you have appropriately described for us. So would you please emphasize that point again?
Sure. And, I think what really captures that is this right here, the fact that our energy needs are increasing, and even though we're increasing our renewable or low carbon emission energy options, we're not increasing them quickly enough, and we're still highly dependable on the burning of fossil fuels. And so if we can find a solution where we have enough options for renewable energy and the portfolio is diversified enough, and we're putting more effort into developing those and continuing that innovation while also considering some of the ramifications of that and the limited resources that are required for those options, that's where we get to a sustainable option and a sustainable future.
With the growth of electrical use, as you were showing it in that one slide where it went from 15 to 26, whatever the P stands for, watts per hour, is there a solution to that? But since we're trying to electrify everything, do you just see that continuously growing? And how do we get renewables or clean energy to keep pace with it? Or can we at this point?
Well, that's exactly what the problem is. That's the constraint that we're dealing with, is that we are increasing our renewable energy sources that is being developed. It's just a matter of how much and how quickly to be able to keep up with the demand, because demand is only continuing to rise.
Okay, Tom,
So
you have a question? And yeah, there you go.
Yeah, sorry to come in late, and wonderful presentation. I guess the thing that occurs to me, and maybe you talked about this earlier, was we need to reduce demand by being more efficient in how we use energy. Did you talk about that?
No, that is definitely a pillar of it. I think at this scale, of a global scale, it's hard to say, other than additional innovation in the technology and how efficiently that energy can be used. It's hard to say societally what can be done at a global scale to reduce that energy consumption, at least from a scientific standpoint in my realm. I'm not a social scientist, so that steps outside of my area of expertise.
Yeah, I'm thinking things like mass transit, for example, moving
Yes, yeah.
to work, more efficient housing, all the things that all the things that we don't do right now. I mean, we're the biggest user of energy in the world per capita.
Yep. So that's another one of those things that could be a full another hour-long talk.
My question, I had never heard about the potential for solar panels actually contaminating the ground, as you described. As you probably are aware, there's a lot of popular opposition in many counties in Michigan to solar panels based on extreme, I would say, even conspiracy theories on the part of some people who are promoting those ideas. And there's a lot of work trying to resist that false, what I believe is false information. And also the state has passed a law which will encourage, will give large solar developments advantages over local opposition. So if you understand the issues I'm talking about, to what extent are the concerns about contamination from solar panels specifically a concern
So, you know, like I said, I spent a lot of time kind of beating down all of these energy options, and there's positives to all of them, and they are necessary for a sustainable future. So I want to reiterate that. I'm not saying that these are bad or we shouldn't do them. Part of why I went through this is so that you guys can be familiar with what might be said to you during your activism and outreach. What's going to be the counterpoints that do have there's truth to them, and those are concerns, and they should be considered. But in terms of the potential contamination from solar panels, that mainly comes from lack of maintenance. So it's going to be an issue more so in areas where the incentive is to start doing it, and there's not a lot of money put towards maintaining it. In Michigan, that's not as much of a concern, but when we consider this globally, then it becomes really variable. In Michigan, Eagle has some pretty conservative regulations surrounding solar panel maintenance. Department of Energy, Environment, Great Lakes, and Energy.
But to tie in with Tim's question, I was reading about how hailstorms can damage the solar panels. That's especially happens sometimes out west more than here, but we do get hail even in Michigan. Would a hailstorm damaged solar panel be more prone to these contaminants leaking out?
If left unattended and exposed to continuous weather events, yes. But again, in Michigan in particular, it's unlikely that they would just be left to rot.
Okay, so one hailstorm would not be able to contaminate the ground beneath it.
I'm not in the habit of using absolute language, but it is highly unlikely. Yes, so I mean, even if they were to get like for some other weird reason, act of God, whatever it might be, just completely obliterated and they're not able to be restored, they are difficult to recycle. In most cases, they would go to a special hazardous waste landfill for that in Michigan, which is another thing that's more tightly regulated in comparison to other states and other countries, where that landfill is going to have specific protections and liners and pumps and a whole wealth of engineering to keep that contained.
Okay, so it's really in the recycle process that we would have to worry about the contaminants, not during normal use.
During normal use in Michigan, yeah, no.
Okay.
Yeah. In the production and construction of them and the mining, that's another part of the equation to consider.
Okay.
They're not commonly manufactured in Michigan either.
Now, I had a question that I've never really seen addressed, all right? We anchor a lot to the bottom of the ocean, and yet the bottom of the ocean is very unexplored. So we have no idea what potential damage we're doing, or do we know what's going on? And because people now are talking about mining the chemicals and minerals from the ocean floor. What effect could this possibly have on global water?
Well, offshore mining is not something that I am incredibly well versed in. At least for the energy options that I discussed today, like for example, the wave energy, that's going to be in areas where the bottom of the ocean is something that we're aware of. It has to be shallow enough for us to actually construct them and go out and maintain them, and also in an area that's close enough land to get wave action, for that to be able to move up and down, and for the generator to actually have energy to convert. As far as deep ocean offshore mining, I don't know that I can speak to the potential global level consequences of that. It's a very big topic.
Okay, it's just something that's been of concern to me since I've been reading that they're think about doing more of the mining offshore, and they're talking more about anchoring wind turbines and all sorts of different things to the ocean floor. And, we have all sorts of creatures that live down there that we're still finding. We don't really understand all the impacts that are being done. And I'm wondering, yeah, and it concerns me because we don't know the future impacts of what we're doing.
Well, and that's kind of the theme of what the talk was today too. So I understand why you're asking that. And, I will say that I probably have some people in my network that might be able to give a presentation on that if that's something that the coalition is interested in enough to have another former colleague of mine come out. I can put you in contact with them.
Okay, thank you.
Yeah, for sure.
Any other questions? So it is 1:06. We are beyond our time. Mary and Ann has been kind enough to keep the Zoom up for us. But are there any last questions?
Yes, actually, I have potentially lots of questions, but first of all, I don't know how often you do presentations, but I find in reading lots of books on climate change, which I have with the climate change book group, often authors or speakers make recommendations about what we need to do, but then not say specifically exactly how we go about achieving those goals. So I like to encourage people when I can, which is not that often, to talk about specific groups. And you mentioned joining organizations. I'd like you to encourage you to mention specific groups. Some of us on this call have been involved with the Citizens Climate Lobby for many years, and are strong advocates for that. We also are involved with the Michigan Climate Action Network, the Climate Change Working Group at Western Michigan University, and so on.
Well, I really do appreciate this.
Of course. Well, thank you all for having me, and I'm so happy to see that you guys are doing what you're doing. And on Tim's point, I came to speak about the things that I know about. I deal a lot with these contamination cases resulting from these things and the high quantity water withdrawals that are when we need a lot of water for this stuff. But you guys are actually the experts in the activism. I just have the science. So, and it's a good point, Tim, and that who exactly to reach out to, what groups to join. That's something that I would get from you guys. So I'm happy to be making this network connection now.
I do have one question, if we have a minute still.
Sure.
They're talking about a new copper mine up on the UP, I think it is, or
Yeah.
that would be actually going under a state park and under the lake. So it's not just going straight down, it's going perpendicular, it's going vertically in two different directions. And could that in any shape, manner, or form do any damage to the water quality up there?
There is always risk associated with mining. So it comes down to the quality of engineering, the quality of the work that's being done, and how conservative the regulations are on both the mining, the construction, the processing, and the monitoring thereafter. So there's existing copper mines in the UP, not that go under a park, but it's not something that would have the same level of risk as being completely new to it in that geological environment. So there's something to look back on and to be able to compare to, at least.
Okay.
But there's always going to be risk with mining, yeah.
Okay, thank you. So thank you, and I guess we'll adjourn the meeting.
Okay, have a good weekend, everyone.